Hey guys, welcome to our walkthrough on Lab 2, which is the buffer lab. Now, this is pages, I think it's 19 through 21 in the lab manual, and that's these pages over here. The other thing that you're looking at right now, these are the pre-lab activities. So what I've got is the one that contains the data. This is the one that I need you to be working with in terms of what you're going to show, okay? So what you need on this is to, there's the introduction on 19 through 22. There's a little video that you're supposed to watch. And then you're supposed to calculate the molarity of the sodium acetate prepared by using 25 milliliters. Oh, garbage. I didn't mean to do that. 25 milliliters of acetic acid and 0.410 grams of sodium acetate. This is the buffer solution, and you need to show all of your work. You want to confirm this concentration with your lab partners and record that in table C. So that molarity is supposed to go right here, all right? So you need to calculate for the 0.410 grams of sodium acetate, which I said, hold on, where did it go? As I indicated, there's a typo in the textbook or in the lab manual. Sodium acetate should be NaC2H3O2. Okay, and that is not what it says somewhere in here. I'm not sure exactly where it is. Anyway, well, there is a typo somewhere because I know that there's an extra thing in it. So we calculate the molecular weight for this, and I showed you that previously with this guy right here. NaC2H3O2 is my sodium acetate, and the molecular weight for that is 82.03. So if I have 0.410 grams, and I'm going to go ahead and move that over because I will do this and I never leave myself enough space. Of NaC2H3O2, that is divided by the molecular weight of that material, which is 82.03 grams per mole of NaC2H3O2. And then to get it to molarity, I need to divide by the volume. Now, we put that into 25 milliliters. And I know that there are 1,000 milliliters per liter. So that's converting milliliters to liters. And where am I going? Oh, hold on a second. Sorry. I seem to have misplaced my calculator. Why? Helps if you actually have the calculator. So 0.410, divide that by the 82.03, divide that by 25, and multiply by 1,000. And I get 0.1999. Okay. So it's not an exact match, but it's pretty close. And that's the number that I need to put right here. 0.1999. Right? So that's that first, so it asks you to calculate that molarity. Now you have data that's been given to you here. You're not going to make any notes because obviously you didn't take this, so you don't have anything that you can write down and say, oh, this happened or that happened. Nothing weird like that, okay? Because that's usually what we record there, is anything that's weird that comes up when we do this. I think that's the only page of this. Then we start into the summary. So your objective for this particular experiment is on page 19. The dissociation reaction for this is on page 19. It's right above equation 1. So it's this thing right here. That's the dissociation we're talking about. The Ka is page 19, equation 1. On my calculations, it says consider the pH of the acetic acids. Using that information, calculate the hydronium concentration of the acidic solution at equilibrium. Well, if you look at the data that you were given on this page, I can get back to it. So if we're looking at the acetic acid solution, the pH of that solution is 2.67. Okay, it's the one that's right here. So that value, the 2.67. So if the pH equals 2.67, calculate the H plus. And of course, H plus is 10 to the negative pH. So I'll let you calculate that. That's how we do that. We set up an ice table to help you calculate the Ka for acetic acid. Use the hydronium ion concentration of the acetic acid solution at equilibrium and the initial concentration of acetic acid to identify all the values required. Should all work in an organized manner. Clearly identify your answer. If I'm looking for something that is clear, I want an ice table. I want that going to H plus C2H3O2 minus. That is my reaction. So that's my R, my initial. The initial concentration that we have for the solution, as we see in the lab manual, because I don't want to flip back through my data. It says 0.2 molar right there on number 4, 0.2 molar, 0.20 molar. We assume that the initial H is 0 and the initial acetate ion is 0. I know that my change is negative X for the acetic acid, plus X and plus X for the H plus and the acetate ion. And then my equilibrium is then going to be 0.20 minus X. We ignore the X. The H plus is 10 to the negative pH. And your C2H3O2 is also 10 to the negative pH. If you want to calculate a K from that value, that's equal to the concentration of H plus times, and I'm just going to write A minus for the anion, over the concentration of HA, which is the acid. So I can plug in the 10 to the negative pH, square that, and divide that by the 0.20 molar. Okay, so that should give you the K from that. Because it does say they want the Ka calculated from the information we got from the acetic acid. We want to repeat that calculation for the hydronium ion and the ice table to determine the Ka using the data from the buffered solution, which is table C. Now, if we go back and we look at the pH of that solution, that's 4.67. Okay, so 4.67. And this table is not hugely different. We still have the same species, H plus C2H3O2 minus. But here's the deal. While that is still 0, the H plus is still 0, and my concentration of the acetic acid is still 0.20, the concentration that I start with of C2H3O2 minus is that number that I calculated, the 0.1999. Okay, so that's a different value. Now, we're still going to get a negative X here. We're still going to get a positive X there and a 0.1 plus X here. And that makes my equilibrium here 0.20 minus X plus X, and here 0.1999 plus X. We assume that the X is small comparative to both of those concentrations, and then we go through and calculate the K again. So again, that's H plus times the C2H3O2 minus all over the concentration of HA, and that is going to be 10 to the negative pH, because that's your H plus concentration, times the 0.1999 divided by the 0.20. Okay, so that's what you should get there, and that should give you a K as well. Awesome. Now, using the Henderson-Hasselbalch equation and the buffer solution data, calculate the Ka of acetic acid. Well, Henderson-Hasselbalch is that pH equals pKa plus the log of the concentration of C2H3O2 minus over HC2H3O2 minus. Okay. I know what the pH is. I'm going to plug in 4.67 for that. I don't know what the pKa is. I have the log of 0.1999 over 0.200, and you can solve for pKa that way. Once you have the pKa, 10 to the negative pKa is equal to Ka. Okay. So going back, the way that we've done previously, so getting between concentrations and K's, P's, so negative logs. All right. Sorry. Trying to do two things at once, which is a bad idea. So that is everything for my summary. Nope, that page of my summary. That's everything for that page of my summary. Still processing video from before, trying to get it all set up for you guys so that you can watch what you need to watch. Okay, so now we want to look at this page. Now, for E, you're going to look up these values somewhere. I need to know what your source was, and I need to know what your value is. Okay, those need to be filled out. You do get points for filling that out. Then we want to calculate the percent error for each of our experimental Ka. So you calculated Ka a number of different times. So you did it here for the acid, here for the buffer, and here for the buffer. Okay, two different ways to calculate that buffer Ka. All right, so we want to look at the B and C, those two calculations. So if the acetic acid is B, the buffer is C. You're going to take the K, so your percent error is equal to the experimental value minus the theoretical value, all over the theoretical value, times 100. And of course, this is an absolute value. So that's how you're going to do that. Now, the experimental value is the one that you calculated during B and C. The theoretical is the one that you have in E. Okay, so that's how you'll calculate percent error for both of those. And remember, the experimental here is the answer from number B. The experimental here is the answer from number C. And both the theoreticals are from E. Okay, so that's where you find those numbers. Now, why would the values calculated using an ICE table and the Henderson-Hasselbalch equation be the same? Well, I want you to think about, how did we get the Henderson-Hasselbalch equation? When we talked about it, didn't we derive that from Ka? And so if we derived it from Ka, which uses an ICE table, then I would expect that they should be the same because they come from the same data. Okay, so that is my expectation there. Now, I'm going to let you explain that however you want to explain that. In the discussion and reflection, I want you to explain why all three samples used in this experiment reached an equilibrium. What does it mean to reach equilibrium? That means that over time I can make the same measurement and get the same number. So when we do this actually in the lab, we take a measurement and then we wait 5 minutes, we take another measurement. Since you only have one value, That implies that it did not change. Okay, so we know that they're at equilibrium because that equilibrium concentration didn't change. Okay, I want you to explain using Le Chatelier's principle how the addition of sodium acetate changed the equilibrium position, resulting in the observed pH data. So what we're talking about is how the HC2H3O2 decomposition to give me H plus C2H3O2 minus. When I add that, what happens to that equilibrium because of Le Chatelier's principle? It should shift. Which way does it shift? And when it does, why does that affect pH? So I think that it should shift this way, which I know that it does. So why does that affect the pH that you see? Why does the pH go up? Because remember, the pH goes up in the buffer. So we need to explain that. In C, the Ka should remain the same for the acid, whether alone or in the buffer solution. Did your results support this? So when we talk about the calculations that we did back here, the value in B and the value in C should be the same. Are they? So compare B and C. If they're the same, great. If they're not, give me some reasons why. Why might they be different? Why? I want real, and human error is never what we're looking for. It could be that one of the solutions is contaminated. It could be that we took the measurement on the pH at the wrong time, so we'd already added HCl or NaOH, whatever. I mean, there are things that could have happened here that we might need to think about. Not clean glassware, contaminated solutions, mismeasurement of the concentration of the sodium acetate, which affects the balance of the acid to base ratio in the buffer. Lots of things can happen. So what might be some reasons that they're different? Okay? And that needs to be specific. So if one of them is too high, tell me why. Okay? If it's too high, what does that mean? That means my H plus is higher than it should be. My acetate ion is higher than it should be. Either one of those is the case. Okay? So that's if that's it. Or if it's too low, what might that mean? So tell me from that perspective what might be going on. So that's everything for your summary. So I'm going to go ahead and close out your summary sheet. And I'm going to go into our post lab. And let's take a look at our post lab. Now the post lab for this, you need to explain the difference between Ka and Kb. We talked about both during this lecture. We talked about what Ka is and what Kb is. Remember, Ka is the acid dissociation constant. Kb is the base dissociation constant. How are they different and how are they related? Why would sodium hydroxide nor hydrochloric acid have an ionization constant? So, for instance, what would the K look like? So that's what it would look like for HCl if it existed, and it doesn't. Why not? Explain to me why not. Okay. Let's talk about the dissociation reaction of HF. You need to write that dissociation reaction. So HF coming apart to give me the two components, the H plus and the F minus. I want you to write the equilibrium expression. So your Ka is going to go there. All right. Now, if the value of Ka is 6.6 times 10 to the minus 4th at 25 degrees, and 850 milliliters of a buffer solution is prepared with 0.650 molar HF and 34.7 grams of NaF, calculate the pH of the buffer solution. So in order to do that, you're going to need to do a couple of things. I'm going to need to take that 34.7 grams of NaF and convert that to moles. And then convert that to molarity. So once you've divided by the molecular weight of NaF, that should get you to moles. Then you divide by the volume to get you to molarity. Then you have a molarity for both the acid and the base. Then you can use pH equals pKa plus the log of the base, which is the NaF, over the acid, the HF, and calculate what that is, all right? So that's what that should look like. You should be able to figure out those calculations. If you can't, I want you to refer back to the summary that we did where I showed you one of those calculations for the sodium acetate, and then use that to do this one. Is this solution an optimum buffer? Okay. What is an optimum buffer? What does it mean to be an optimum buffer? We talked about this before. An optimum buffer has the same amount of acid and base. So the NaF and the HF should be the same if it's optimum. Is that true? Yes or no? So you need to figure that out. What was the pH of the solution before the NaF was added? So with that 0.650 molar HF and the Ka, calculate the pH from just HF decomposing to H plus F minus. Okay, so I want to know, what is the equilibrium for the H based on the concentration that you started with, which is 0.650 mole. Okay, so what is that H plus that goes with that? All right. And again, this is provide the name and chemical formula of a salt that could be added to a solution of nitrous acid to produce a buffered solution. So nitrous acid is that HNO2. If I need to make a buffered solution and I have an acid, I need to add something to it to make a buffer. So what do I need to add? Hint, hint, conjugate base. So what is the conjugate base of HNO2? And then how would I get that anion into solution? Okay. Sodium salt is a great way to do that. And then if a 0.150 weak acid HX combines with potassium salt KX to produce an optimum buffered solution with a pH of 8.45, use a Henderson-Hasselbalch equation to calculate the Ka of this weak acid. So let's talk about this for a second. So we have HX. It decomposes to give me H plus and X minus. Okay. I know that I start with a 0.150 molar. This is 0. And then I have a potassium salt KX to produce an optimum buffer. Okay. So I have some amount. I know that pH is equal to pKa plus the log of the base over the acid, where the base is that X minus salt and the acid, which is the HX. Okay. Now, if it's an optimum buffer, we know what that relationship between HX and X minus is, because we defined an optimum buffer earlier and we said what that meant. So if I know what that means, that should tell me what this log value is going to be. All right. And if I know what that log value is going to be, then my pH should equal the pKa, because that's log should be 0. All right. You need to explain to me how that happens. But then you should know what the pKa is. And from the pKa, you should be able to calculate Ka. Okay. So those are all the hints and directions and stuff that I'm going to give you at this point. I hope that you have enough information to be able to go from what you have to what you need. So I'm going to stop sharing. I'm going to stop this video, and I will get this posted so that you guys can see it, and then we'll be off to the next lecture. Thanks, guys.